Yo, what up everyone? This is LeetCode 104, maximum depth of binary tree. Given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So yeah, you just have to find the longest path essentially and count the number of nodes along the way. So you're basically finding the height um but the maximum possible height. So in this case, it would be 3. I mean, you can use different approaches for this problem. You can solve it recursively. You can use BFS. You can use DFS. I'm just going to use an approach that I've used in a previous problem, only because I went super in depth in that video. And if you're still lost after my explanation in this video, you can look at that video, and I think it'll be more helpful. So that's why I'm going to use this specific approach that I'm going to show you now. But be aware that there's a lot of approaches to this problem. So if you can come up with a different approach, that's totally okay. Right? Just make sure the approach is not pay attention to time complexity and stuff. But anyways, so this problem, I didn't solve this exact problem before, but I've solved a problem called diameter of binary tree. We've done a video on that before, and it's LeetCode problem 543, and I have a long video on it, and it might be super useful to check that out if you're still lost on this problem after I explain it. But basically, in that problem, we were counting the diameter, right? How far the tree essentially spreads. But the reason that problem is relevant to this one is because we did a bottom-up approach in that problem, and we were counting the height, right? And so we were counting the height and then using that to kind of account for the diameter of the tree. Well, we can use that exact same approach not to account for the diameter of the tree, but to account for the height. Okay, and so that's what we're gonna do. Okay, so we're gonna define a a function called DFS. Okay, we're gonna define a function called DFS, and we're gonna pass it the root node. Okay, now if the root node is none, we're gonna return 0. Okay, and I'll go over this algorithm after we're done, but just be aware that we're working bottom up, really. That's what we're doing to count the height. Okay, so we're gonna say left is equal to DFS of root.left. Okay, and I'm gonna say right is DFS root.right, and then we're gonna return 1 plus the max of the left and right. Okay, and then we're going to down here we're gonna actually call the function starting at the root node. Okay, so what we're doing, I'm gonna use this example here. Okay, we're starting at 3 and we're going left. Okay, because again we iterate all the way left. We keep calling root.left. Okay, and then root.right when we return 0. So let's go with this example. Okay, we start at 3, which is the root node. Okay, and then we go left, DFS root.left. Okay, then we go DFS root.left again. Okay, now we're returning 0, right? Because 9 has no child nodes. So when we're at 9, we go root.left and root.right. We return 0. Or yeah, we're down here. Well, this node is null, so we're going back up and returning 0. When we return 0, okay, left is going to be 0. Right is going to be 0. Okay, makes sense, right? Because 9 has no child node, so how could any of those child nodes contribute to the height? Okay, now we're going to turn 1 plus the max of the left and right. Well, 9 has no child nodes, right? So the left and right is 0. So when we go up, we're adding 1 plus the max of left and right is just 0, right? Left and right are both equal to 0. So the max that we can get is 0. So when we're at this 9 and we go up, we're returning 1 plus 0. Okay, which makes sense, right? Because from 3 to 9, it's only a height of 1. Okay, now we're back up at 3. We're gonna go from this 3 to this 20 to this 15, and then this 15 we're gonna go root.left. We're gonna return 0. Then at this 15 we're gonna go root.right. We're gonna return 0, right? Because it has no child nodes. So when we're at this 15, we're going to go back up and return 1 plus the max of the left and the right subtree. Well, at this 15, the left and the right subtree is 0, right? Because it has no child nodes. So we're basically going to do 1 plus 0. So when we're at this 20, the left subtree height so far is 1. Now we're at this 20, we're going to go to the 7. Again, 7 also has no child nodes. So when we're at the 7, we're going back up. We're going to do 1 plus the max of the left and the right. The 7 has no left and right child nodes, so it's going to be 1 plus 0. Okay, at this 20, when we go up at this 20, we're going to do 1 plus the max of the left and the right. Now, the left and the right are not 0, they're 1, right? 20, the left is height, the height at 20, the height for the left subtree is 1, or the max, I should say the max height so far. At this 20, for the left subtree is, the height is 1, at 20, the right subtree height is 1. So really, when we're at this 20 and we're going back up, we're just doing 1 plus the max of the left and the right. Not really a big deal because left and right are the same. They're both 1. So we're just doing 1 plus 1. But let's say this tree was structured slightly differently, that this 7 maybe had an actual node. Well, at that point, the height of this 20, the left subtree height would be 1, and the right subtree height of this 20 would be 2 in that theoretical, hypothetical case, right? And so if that were the case, we would do 1 plus the max of the left and the right. Well, the right is the max, which would be 2, so we'd do 1 plus 2. Right? Again, it's a hypothetical, right? Because this is balanced. This subtree here is balanced, meaning it has the same height for the left and right subtrees. But anyways, at this 20, right? Left and right are 1, so we're going to do 1 plus the max of the left and the right. Well, left and right are the same, so it doesn't matter. But so we're going to do 1 plus 1. We're at this 3, and we're going to return 2. Okay? Well, when we get to this 3, we really should be what? We should be returning 1 plus the max of the left and the right. Well, at this 3, the right, or sorry, at this 3, we're at this root node, right? We've already done all the child nodes of 3, okay? So at this 3, this root node, the left subtree max height is 1 here and 2 right here, okay? So when we're at this root node, we're gonna do 1 plus the max of the left and the right. Well, the left is 1, the right is 2, so we're gonna do 1 plus what? 1 plus 2, right? Because this is a bigger height than this, okay? So we're going to do 1 plus 2, and we're going to return 3. Well, that makes sense, doesn't it? We get the right answer. We're returning 3, okay? So I hope that's clear, right? I tried explaining it as best I could. Again, we've done a similar approach to a different problem called diameter of binary tree, LeetCode problem 543. I have a video on that, so if you're still lost, I encourage you to watch that. Very similar approach where we're working bottom up in a tree, counting the height. But yeah, so yeah, that's all we're doing. We're working bottom up and just counting the height and finding the maximum height that we've seen so far. So that's how we kind of find, quote unquote, the longest path, right? Okay. And again, there's a lot of ways to approach this problem. I just really love a bottom-up approach. It's very intuitive, very simple to understand. And I mean, you can just reuse the same approach for different tree problems if you need it, right? In regards to the height, if you need the height for some reason for a specific problem. But yeah, yeah, I think it was pretty simple. But yeah, like I said, I have another video on it. So, right. LeetCode 543. I've done a problem on that, so if you're still lost, please check that video out. It'll be really helpful for you, but I think I explained it pretty decently here, right? We're just working bottom up and tracking the heights, okay? The maximum heights for the left and right subtrees, and we're taking the max of the left and the right subtree as we go up, okay? Hope that makes sense, and I'll see you in the next one.